Let's begin. Last time we left off, I wanted to cook the lobster. Mr. Larry, the lobster, wanted to cook the lobster in Python together, but we didn't have a chance to do that. Today we're going to do that. I'm going to pick up the pace a little bit faster because there's a lot of material I still need to cover by the end of until the end of the semester. So what we're going to do regarding the homework, there's going to be a homework assigned today, which was already assigned, and a homework assigned next Thursday, but those are not going to be due until 3 weeks from now. So take your time, start working on them, because some material I would have already covered, some material I wouldn't have covered yet. So take your time as you do the homework, but start working on them as soon as you can. Yeah.
3 weeks meaning during finals week or after?
Before the final week, before the week of the finals, they will be due that week. Okay, that Thursday. Okay, so that you at least finish them, and we can provide a solution for them before you get to the final exam. Okay. All right. So last time we left off talking about ordinary differential equations. We were focused on initial value problems or propagation problems, or IVPs, initial value problems, IVPs. And I introduced to you this built-in routine in Python called odeint. It stands for ordinary differential equation integrate, which is essentially another meaning of solving an ordinary differential equation. odeint takes an arbitrary differential equation, an arbitrary first-order initial value problem of the form d phi by dt equals some right-hand side that's a function of phi and t. Phi is the dependent variable and t is the independent variable, or the time in this case. And it takes 3 arguments at a minimum to get started. So that's where I finished off the lecture last time. The right-hand side, as I discussed, is just simply the name of a Python routine that implements the right-hand side of your ODE. All of these ODEs, they look the same. It's d phi by dt, or du by dt, dt by dt, dp by dt equals something. That something is what matters to how the solution is going to look like. So it lends itself for a really nice way of generalizing the solution of differential equations numerically. So this RHS is, think about the residual function when we were doing fsolve and nonlinear solvers. All we provided fsolve was the name of that residual routine. Same thing here. You just provide the name of your right-hand side function for the ODE. So for example, it would look like this. But make sure that the order of the variables, the first variable is the dependent variable here, the first argument. The second argument is the independent variable. Okay? And Python takes care of the rest magically. Phi 0 is an initial condition, and t is an array at which you want the solution to be computed. Okay? T0, T1, T2, however you want to space those. You could use, you can hard code those at the different times you're interested in. You could do a lin space, you could do a log space, however you want. And odeint will find the solution at those points for you as a guarantee. And the answer, so odeint returns a bunch of numerical values that contain the values of the solution at those different times, T0, T1, T2, and so on. So if you recall a few slides earlier, we said that that's our plan for the solution, is we're going to subdivide the time space into intervals, equal or unequal. They don't have to be equal. It's just easier to discuss them when they're equal. And then your objective is to find the discrete values of the dependent variable at those times. So that's what odeint is going to give you. You give it this sequence, you give it the right-hand side, and odeint is going to give you phi 0, phi 1, and so on. Okay, perfect. So now we're done with that. We are going to, together, bake the lobster in Python. And remember, we discussed 2 approaches that, as an engineer, you were supposed to investigate. Cooking the lobster, you want the fastest way to get that lobster to a cooking temperature. I don't know, maybe 350 Fahrenheit or something for a properly cooked lobster. And we had 2 options for these differential equations. The first option, boiling it in a liquid, water, oil, or steam or something, right? And the ODE looks like this. I explained that at length last time, so we're not going to go over it again. or baking it inside an oven, and the ODE is different. You still have dt by dt. This capital T is the temperature of the lobster, lowercase c is the time. And when baking it in the oven, you notice that there's a T to the power 4 here, whereas here is just T minus T infinity. T infinity is the ambient temperature, either of the liquid that's boiling or of the radiating environment inside the oven. All right, so grab your Python notebooks and let's do this together. I'm going to create a new notebook. Let's move it to the side. Okay. Cooking a lobster, Python. Larry, cooking Larry the lobster. Lobster in Python in class activity. Okay. I'm going to import the boilerplate. Just by now, just copy paste, right? Copy paste NumPy. We're going to need NumPy. We're going to need matplotlib. But I'm also going to import odeint. So from scipy.integrate import odeint. Okay, so odeint is going to be our go-to routine. It will be your go-to routine to solve ordinary initial value problems. Okay, so with this procedure, we want to define only the right-hand side for odeint. So if you recall here what I had, where is that? Where is it? Where is it? Where is it? Okay, it's right here. So all I need for odeint is to define, remember I need a right-hand side. I need one right-hand side for boiling it in a liquid, and that's going to be minus HA over MCP T minus T infinity, and another right-hand side for baking it inside the oven. Okay? So let's do that. And I'm just going to, I'm going to need L, R, A, and all of those quantities. So I'm just going to hard code those inside the right-hand side routine. Just like we did with the residual functions, we'll start there, and I'll show you later a way of circumventing having to hard code things like that. All right, so we will start by defining right-hand side for boiling it in liquid. Let's call it right-hand side boiling. And by definition from odeint, the first argument needs to be the dependent variable, and the second argument needs to be the independent variable. So I'm going to put t and lowercase t, okay? Or call it time, right? So this first t corresponds to the dependent variable. So when you implement the formula, you're going to grab that first argument and treat it as the temperature, okay? That's what matters, the order, not the naming of the variables. It's the order. The first argument is always the dependent variable. All right, so we will put first our heat transfer convection, heat convection coefficient. We'll just put 100. I'm going to omit the units here for to make things to go faster. Length, radius of the lobster, 0.1, so about 10 centimeters. The area was 2 times pi times r times L, right? So 2 pi RL plus 2 pi r squared. Okay, 2 pi RL plus 2 times pi times r squared. Okay, and the mass was 1 kilogram. The heat capacity or specific heat was 4,200 joules per kilogram Kelvin. You know, I'm omitting the units here. Just trust that the units are consistent. And our T infinity here, we're going to start with T infinity equal 374. So that's the boiling temperature of water. Boiling temperature of water. And you see, as we are going to explore different liquids, we will change H and T boiling, T infinity. That is going to affect how fast that lobster is going to be cooked. If you have a strong driving force on the right-hand side, it's going to cook it faster. Okay, and it's going to get it to a higher temperature. All right, so those are the parameters that we will play with for a fixed lobster size. And then the right-hand side, or the result, is going to be minus h times, so you just write the formula, HA over M CP. So over M over CP times T minus T infinity. Look, guys, couldn't be any easier than that. What is this T? It's what you're trying to compute. You're bringing it through here. It's coming as an argument, and Python figures out how to pass it to you. It's just going to give you a value. Don't worry what's happening behind the scenes. We will study that later. Okay? But for now, trust that these two arguments in this order, the first argument corresponds to the dependent variable. The second argument corresponds to the independent variable. I don't have time in my right-hand side, so I'm never going to use that variable. But you have to define it this way. That's what ODEint requires. Otherwise, it will crash. Because ODEint, when it calls the right-hand side, it's going to pass to that right-hand side two arguments. The dependent variable, comma, the independent variable. Whether you use them, some ODEs don't have a dependent variable on the right-hand side. So you won't use the first argument, you'll use the second one. And then you simply return it. Recall what we did with fsolve and the residual function. Okay? Exactly the same procedure. Okay, so that's right-hand side boiling. Let's do now define right-hand side baking in the oven. Okay? And again, T and time. And I will need the same specs over here, H, L, R, and M. So if I come back here, there's minus sigma epsilon A over MCP. So I will need area, mass, and specific heat. So I need all of those actually here. I don't need H because there's no heat transfer coefficient here, but there's a Stefan-Boltzmann constant. So that's sigma, which was 5.6704 e to the minus 8, right? 5.6704 10 to the minus 8. And this emissivity, epsilon, I'm going to set it equal to 1. T infinity for the oven, let's say you're baking at 425. You could go to broiling, 550. You could go to kind of almost like air frying at 390. It's a parameter that we are going to change to study which one is going to be faster. Okay? So that's the whole point of it. We're kind of using the ODE as a venue to reverse engineer what material we need to use to cook the lobster in. T infinity, let's put it at 450. So that is Kelvin oven temperature. Okay? And again, this is a very rudimentary model, but boy, it does such a great job at getting the answer. All right, so right-hand side is minus sigma times epsilon times A over MCP, right? Times T to the power 4 minus T infinity to the power 4. Finally, return right-hand side. ODEint does its magic internally. All you have to do is just give it one of these right-hand sides, and it figures out the rest. Okay. Are we all synchronized? Yes?
So why do we include time again if it's not used?
Because the interface for ODEint requires that the right-hand side function always has at least these two arguments. It's a requirement by ODEint. So whether you use it or not, it's inside ODEint, it says call right-hand side with dependent variable, independent variable. If you were to create a right-hand side with only one argument, it's going to crash. It's going to tell you, well, I don't have room for a second argument. So ODEint is requiring that.
And T, capital T, is the independent variable in this case?
Temperature, yeah. sorry, yeah, capital T is the dependent variable. It's the temperature, right? And so the way to think about this requirement is that the first argument is the dependent variable, the second argument is the independent one. So that when you come into your formula here, you treat the first one as your dependent variable, your second one as your independent one. If we had time here, let's say we had time sine t, time, right? Then you would take time and put it here. And then that just works nicely. If you swap the meaning, you're not solving the correct ODE, you're solving something different. Okay? All right. Actually, we're ready to solve this now. So I'm going to put a title here because I know what's coming next. Using ODEint. Okay. So let's say we are going to cook them for, let's say our time space is going to be 20 minutes. Okay? 20 minutes. We're going to see what happens in 20 minutes. Will someone Google, how long it takes to boil a lobster in water and how long it would take to bake it in an oven? So let's just see.
Lobster is 7 to 10 minutes for 1 pound of lobster.
Okay, 7 to 10 minutes boiling. All right. Okay, and for baking in the oven?
This is the 12 to 15.
Okay. 12. All right, so 20 minutes. Let's pick 20 minutes. All right. Now, since the units here are so ODEs are generally, in many cases, they give you the ODE in dimensionless form. Time, etc., they just are all dimensionless. But in this case, T is in seconds, actually. You can change the meaning of T. You can make it in minutes. You have to change the coefficients, though. Okay? But in this case, T is in seconds, so I have to make everything in terms of seconds. And so I'll do my T end as my end time, let's say 20 minutes times 60. So that's 20 minutes times 60 seconds per minute. So that I know how many seconds I'm running for. And then I will create my time space. Time space, let's say. And that's going to be np.linspace. So I'm creating now those time intervals. And I'm going to create them of equal size. Okay? There's no preference otherwise. But there are cases where you don't want them to be equal size. We'll talk about that when we get to implicit methods. So numpy.linspace, and I'm going from 0 to t end. And I will put, let's see, 300 points. Okay? Now you're going to ask, how do you choose the number of points? We're going to get to that. However, ODEint is smart enough that it will still give you a solution even if you put a bad number of time steps. Turns out that there's a limit there's an ideal number of time steps that you have to put in that time interval. That goes beyond what we need to know, really. But for now, that's why I love to teach ODEint, because it kind of hides some of that. We'll talk about those issues when we hit implicit integration, okay? All right, so now, and my initial condition, let's say it's coming out fresh from the freezer. So that would be like, what, 310 kelvins? 310 freezer temperature. Okay, so that's the initial condition. And that's it. I'm going to call ODEint. Now, if you open the brackets, you see the function signature. Your right-hand side, your y0 and t. Those are the 3 minimum arguments that are needed. Okay? And if you scroll down, you see a lot more detail about what's going on. And notice here, so that answers your question again, that function is a callable Python routine. It takes the dependent variable. They are forcing me to choose that. Y and t. Okay? Y, dependent variable. T, the independent variable. Okay? So I'm going to call ODEint. The first one is going to be on boiling. All I need to do is give it RHS boiling. Okay? And then T0 and the time space. All right? Now the answer, I want to put it in an array. Because if I call ODEint this way, it's going to give me a sequence of temperatures at all the time points. So this time space has 300 points starting from 0 to t end. Okay, 0, 0.01, 0. Whatever, right? So I want this ODEint is going to give me the solution at all of those points. So I'm going to store it in an array, and I'm call it t boiling. So that's the temperature of the lobster if we were to boil it. Okay? So this is Larry's temperature while boiling. Okay? Same thing for tea baking in the oven. ODEint, RHS baking, again, same initial temperature and on the same time space. So it's like we have the same, we clone the lobster, it's the same size, same age. One of you cooks it with boiling in water, one of you cooks it in the oven, and start the timer. Let's see what happens. Okay? Now if I run this, yeah, it ran, but we haven't seen anything yet. So let's go ahead and make some plots. I'm going to plot plt.plot. I'm going to plot the temperature versus time, right? Because that's what you're solving, temperature as a function of time. Agreed? So I'm going to plot the temperature versus time, and I want to express my time in minutes. So on my x-axis, I'm going to put time space, but I'm going to divide it by 60. So I get back to minutes instead of seconds. Time space was in seconds. Now I want to convert it to minutes because it's more human friendly to read in minutes. Oh, it took 1,735 seconds to cook it. Well, you know, it's kind of very hard to conceptualize that, right? And we will do tea boiling first. Tea boiling. And we'll give it a label. Say, boiling Mr. Larry. Okay? And for radiation, for baking, tea baking, and we're going to say baking Mr. Larry. It's going to automatically assign a color for that. For the x-axis, plt.x label, let's say time in minutes. And plt.y label, let's say temperature in Kelvin. Okay? And let's add a legend. And let's add a grid. All right. If you have this, go hit it, run it. Let's see what you get. Did you get something? You're guessing it's not right?
Yeah, definitely not right.
Okay. So you made a mistake in the right-hand side probably. Double check your right-hand side. This is what I got. If you didn't get this, we'll help you. Did you get this? Gorgeous. Yes. Uh-huh. Yeah, for the right-hand side, you'll probably have an error in the right-hand side. Okay? I want to laugh. It's just instantaneously incinerated. There's nothing left of Mr. Larry. No, right-hand side freezing, okay. So you have an issue with the right-hand side, you're cooling it. Okay, you guys got it here? Okay, you got it. It's off quite a bit. Yeah, it's off quite a bit. Look at your right-hand sides. Maybe a sign problem. You got it? No? You got it? Oh, okay. 2 pi r squared, 4,200. Oh, you put h is 500. Put h 100.
Okay.
Yeah. Yep. You still can. Yep. There you go. Yeah. 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 Okay. So I know you might be working within. No, still issues. Okay. Did you get it?
Yeah.
Okay. Awesome. Return. Yes. Oh, still an issue. So it fixed one of them. So you have the issue with the boiling. Oh, you got to return. Yeah. That's important. Yay! All right. Victory is ours. Okay. All right. So how can we, let's start thinking about this plot. In the end, I know you might be so passionate about the math and the coding, and I'm like that. But that doesn't matter if you cannot draw a conclusion from your plot. Okay, so when you look at this, you're saying, okay, what are we looking at? Each one of those curves represents the temperature. The blue one is the temperature of Larry while you're boiling it, and the orange one is while you're baking Larry. And the x-axis is time. So this is the temperature of the lobster as it is being cooked. Okay? It starts, both of them start from the 310 degrees, right? So that's good. They're starting from that same initial condition. And as they heat up, their temperature, their body temperature picks up, right? And then eventually you look at the blue curve first. Look at that. It starts heating. It has a higher slope than the radiation, than the oven temperature. Okay, but then it plateaus. Why does it plateau, and where does it plateau at? Okay, look at the right-hand side. Remember the population problem we did last time when we had the switch. What happens when t is equal to t infinity? The right-hand side becomes 0. So then it's going to go flat. Right? It's going to go flat. Same thing is going to happen with the oven. However, the oven temperature is the infinity, T infinity for the oven is way higher. So it's going to allow Mr. Lobster to keep cooking until you hit that very, very high temperature. Okay? However, let's say what is a good, could you Google like what is, cooked temperature for lobster, please? 335 maybe? What is it? 150, one what? 145 Fahrenheit. So in kelvins? 333. Okay, so wasn't too far off. Okay, so let's say I'm going to draw the line of when we say it is cooked. Okay, so this is an x line. Y is equal 330. Say 335, and line style, let's say, is dash dot. Okay, so this is the temperature when we say the lobster is cooked. Okay? Now, obviously, you put it in the boiling water, it's going to reach that temperature. You don't take it out because it's not going to be uniform in reality. Okay, so we're quite off from the actual numbers that you quoted where it says 7 minutes for a 1 pound lobster, but this is a heavier lobster. This is 1 kilogram, so it's probably like what, 2.5 pounds or so, right? So it's a little bit heavier, this one, but actually it's predicting much smaller. So the model is a little off, okay? But it does give us a sense of how the temperature change looks like. Okay, it could be because of the assumptions we made or the model parameters that we haven't kind of really fine-tuned the model parameters correctly to get the right numbers. But still, the point is you have reached this temperature with boiling sooner than you did with the oven. Okay, so let's change things a little bit. What if you choose a fluid, okay, with a much higher heat transfer coefficient or much lower one, right? So let's say you go to cooking oil. Cooking oil has much higher H values, so it's going to cook it faster. Or if you go to air frying or kind of steaming, that's going to lower that H, but it's going to allow you to get to a slightly higher temperature. So let's say you go to H equal 10, for example, but your T infinity is 400 with boiling, okay? And then with the oven, we're still at, let's say, 450, so we're good there. And you do that, then now, well, it's going to look much better for baking it in the oven. We're going to hit that desired temperature sooner. Now, clearly, you don't take it out once you hit that temperature, because it's not going to be entirely uniform. We're assuming it's going to be uniform, part of the assumption. But you don't take it out immediately. You let it sit for a few more minutes, right? But it's going to give you a sense of what you can do when cooking the lobster. And by changing that H parameter and T infinity, that will allow you to choose different fluids. So you can go open your textbook and say, or open some reference book and say, okay, what are the properties? Like, so for example, you can Google, Tanner, I'm like hammering you with Google requests. So like you Google heat transfer coefficient for different oils or liquids, right? And you can see their boiling temperatures. So oil is going to boil at a much higher temperature. So it's going to allow you to heat the lobster to a higher temperatures, right? Because T infinity is going to be higher, for that, but it's going to have also a much higher heat transfer coefficient. Okay, so we go 500, let's say, then you're going to have a much faster cooking trajectory for the lobster. Okay? That's it. That's what ODEint can do for you. You can now solve ODEs. So you go to your ODE class in math, use this on the side to try to understand what your ODE is doing. If it's a complex ODE with a complex analytical solution, you're like, I have no idea how it's behaving, this will help you to shed insight. Plug in some numbers and see what happens with that ODE. Okay? All right, so let's get back to the slides. Okay, so I have the code in the slides. It's recorded. Everything is here. Okay. So now I want to augment your ability to using of how you use ODEs, ODEint. And you probably, it was kind of relatively easy to go change H and T infinity, etc. But it might not be the best way to do it every time to go into your right-hand side routines and change the values. What if you change them inconsistently? What if you need to change the length and the radius of that lobster? You have to change it in both spots, in the right-hand side boiling, right-hand side baking. What if you had other routines? So you're going to commit an error. What you want is really one interface where you could say, study the lobster properties at this L, at this radius, and at this heat transfer coefficient, and so on and so forth. You might argue, let's just declare them as global variables. For a simple problem like this, you'll get away with it. Nobody's going to fuss about it. But for real kind of high quality production code, you do not want to use global variables. Okay? Don't use global variables. It's out of the question. Year after year, we have claims that say, it's okay to use global variables. Then we do another study, another research, and we discover all sorts of bugs that cause serious crashes in serious code that could actually cause harm, actually destroy structures because of misuse of global variables being redefined, etc. So don't use global variables. All right? Okay, I'm going to show you now a trick. Just like we did with fsolve, where we were able to pass additional arguments to the residual function, we can pass additional arguments to the right-hand side. And the idea here would be, if you wanted to pass like the heat transfer coefficient and T infinity for the boiling, and you want to change the emissivity or the T infinity for the oven, you don't have to go to the right-hand side routine. Okay, you just send it, pass it as part of the arguments. ODEint allows you to do that just like fsolve. And so if you look at ODEint, you have the first, so let's say your right-hand side is defined as phi, t, and it's got a bunch of parameters. This could be the heat transfer coefficient, radius, or whatever, a bunch of parameters. You could have 50 of those. Doesn't matter. Okay, your right-hand side depends on those. Then with ODEint, you still use our standard approach, right-hand side, initial condition, time space, but then you can add those arguments and call them, pass them from ODEint. Because the idea is that you are controlling ODEint. You wrote the right-hand side once and for all. You put that in a file. You don't touch it anymore. But then you keep reusing it over and over again. And all you do to change the behavior of the right-hand side is pass it the arguments. So if you add this argument here called args, and you pass them as a tuple, okay, in these parentheses, then you can pass those arguments to the right-hand side. Okay? So let's try to do that with Python, since we have this already. Passing arguments to the right-hand side routines. Okay, so I'm going now to redefine these right-hand side routines. And I'm going to pass the heat transfer coefficient H and T infinity. You can pass S, L, R, A, L, and R, and M, and whatnot. I'm just going to do these two for now. So then when you pass them in, you don't need them here anymore. Okay, those are coming in. Those are coming in from ODE int. Okay, and let's do the same thing for baking. And for baking, all I need, I just want to pass t infinity. Okay. All right. So now we've redefined our right-hand side. Let's call it RHS boiling 2. Very creative name. RHS baking 2. So all I did, I added arguments to the right-hand side. Your right-hand side might depend on more parameters. Not variables, they're parameters. So I distinguish between variable and parameter. Parameter is something that is not part of the evolution of the equation, but it affects it. It's a coefficient, it's a property of the domain, of the lobster, of whatever device you're working with. So you can set that as a user or an observable property. It's not a variable, it's a parameter. So t infinity and h and t infinity here. And I'm just really just copying and pasting. So I'm going to go again here and copy and paste this, all of this, into a new cell. Okay. What's going to change here is RHS boiling 2 and RHS baking 2. Right? And then my third argument is going to be args equal. Okay, so for RHS boiling 2, the next one was going to be h and then t infinity. I'm going to put, let's say, 100 for h and 390. Okay, and then for baking, args is equal to, we had one argument, which was t infinity. Let's say we're going to broil it at 550. Okay, well, Fahrenheit, Kelvin. Okay, and then you run it, and you get an error. RHS boiling 2 is not defined. That was intentional, so. You still get an error. RHS extra arguments must be in a tuple. Okay. Where is it? So it's probably this one. Okay. Okay. So it's panicking about this one. So all you have to do is just put a comma here and do nothing, and then it should just work. Okay. And so with that, now all I have to do is change my parameters here. I can change h over here and see what happens. And rather than having to go back and forth to the right-hand side, okay, and edit things inside the right-hand side. Okay. Next year, I'm going to fine-tune the model a little bit so that we get the right baking temperature. I think the numbers are not perfect. To just kind of try to get it to fine-tune it to what you see in Google for the baking. Okay, so it's similar to fsolve, what we did in fsolve. You want to pass additional parameters, you pass them this way. Don't declare global variables. Okay, even if you're baking one lobster, which has the same length, area, and whatever. Okay. Put those in a routine, right, and declare them inside that routine, call ODE int. No global variables except for pi, maybe. Okay? Okay. Going to let this go now and continue with what's next. All right, so ODE int has been super useful in solving a single initial value problem for us. Next, we are going to use it to solve a system of differential equations, system of initial value problems. Those are coupled, multiple initial value problems coupled together. Okay. But first, you'll notice that you will see systems of equations in kinetics, in like mass conservation systems, etc. Once you take your kinetics course next year, you'll see kind of when you have a reaction mechanism, there's like 7, 10, or 50 ODEs all coupled together. And you're going to use ODE int. Thankfully, ODE int allows you to solve a system of equations. You're going to see that you're going to use that in that course again. Okay? But how do these systems of ODEs come up from? Thankfully, for initial value problems, there's a great analogy for how you can build these ODEs. And it's called compartment model theory, or the compartment model framework for initial value problems for differential equations. And the idea is simple, and I kind of try to fine-tune it to something we can understand here, or something easy to think about. I'm going to consider a department store, Macy's, Nordstrom, whatever, Burlington, not Burlington, maybe Macy's, okay, a department store. Now, the store has a number of people in it, shoppers, employees, solicitors, etc. Okay, there's a bunch of people. For some reason, there's some babies floating around here, kids running around, just people kind of hanging out at different levels of that store. Okay, there's people inside that store, right? We're going to designate by n as the total population inside the store. So n is the number of people inside that store. Okay? The store also has an entrance or multiple entrances and an exit or multiple exits. Okay? So now it's kind of obvious that the rate of change of people inside the store depends on how many people are coming in and how many people are leaving, right? So the rate of change of the population, n, depends on how many people are entering and how many are leaving. Okay? If people are leaving the store, then we expect the population to decrease. So what does that mean for the time rate of change of n? Negative, yes. It's amazing how 5 minutes of thinking about ODEs in this way is going to explain all ODEs for the rest of your life. Seriously. But for initial value problems, okay? For initial value problems. All right. So Tanner's right. If people are leaving the store, then we expect the rate of change of the population in the store, or dn by dt, to be negative, and to be exactly equal to the rate of people leaving. If 2 people leave per second, then dn by dt is going to be minus 2 people per second, right? And so in general, we write this as dn by dt is equal minus rate of people going out, minus r out. R is a rate of people leaving. How do you count that? You go and measure. You just kind of put a counter. Maybe on average you measure for an entire day, and on average you say, oh, in the early on there were not many people leaving, but then later in the day there were more people leaving. Then maybe that rate is a function of time, right? Or you could average it over the entire day, but it doesn't matter. The fact is that still dn by dt is minus the rate of people leaving that store. The larger the population inside the store, the more people are likely to step outside. This means that the rate of depletion, that's one model to think about it, the rate of depletion is proportional to the population size itself. Okay? So you could say, well, okay, if I'm not going to measure that, I'm just going to try to model it in my mind. I could say that the rate of people leaving is proportional to the number of people inside the store. So I'm setting the stage here for the COVID model that we're going to develop together in a minute. The more people that there are susceptible, okay, the more likely that they're going to be infected if there's an infected person between them, right? So it makes sense that the number of infections is going to be proportional to the number of people who are present among, in the room or whatnot. Okay. So that's one way to think about this, but this is only one option for minus r out. The fact you still have minus r out. The population is decreasing. Okay, now let's take the other side of the other door. When people are entering the store, then we expect the population inside the store to increase, right? So you expect that dn by dt to be positive, right? And we write this as dn by dt equal rn. Okay? It's a balance. It's a simple balance. That's what initial value problems are. When you hit kinetics next year, this is exactly it. One reaction going to another is going to balance. There's like, okay, I'm increasing the concentration of this reactant, and I'm decreasing that one. So there's a balance between the two. So the rate of change is one is going to go up. The rate of change of the other is going to go down. Exactly like this department store. Okay? The more people that are outside of the store, the more likely are going to go in. So if you call the population outside the store I, then you could say that dn by dt is beta I, where I is the outside population. You could say, okay, the outside population is 7,000 people at any given day. Okay? All right. But in general, you still have that dn by dt is equal to the rate of people coming in minus the rate of people coming out. That's your balance. That's your mass balance equation, really. But now written in terms of a differential equation. That's it. That's what I want to talk about how you build ODEs. So now let's do a concrete example and build a model for epidemics. So we built this when COVID hit in 2019, 2020, we were shut down. We're starting ODEs. So I put this model, there's in the literature, it exists in the literature, and then we built on top of it. But I want to show you how they built it. It's really nothing that complicated, nothing that any one of you cannot do. Okay, so we are going to consider, in the simplest form of this model, we are going to consider 3 parts of the population. Okay, there's a total population, number of people, n, but we're going to consider 3 compartments. Okay, that 3 department stores, if you like. Okay, so we're going to split the total population into 3 department stores. The susceptible population, those people who are not infected, but they're ready to get infected. Those who are infected, and those who have recovered. Those are 3 department stores. Each department store has an entrance and an exit, or just an exit, okay? Or just an entrance. All right. There's only one way for the susceptible to move from the susceptible department store to the infected store, right? There's no, we're assuming that population is just because we locked down everything, nobody is coming inside the state or out of the state, right? That's the entire population, right? So they're all susceptible, let's say. So there's only one way for susceptible people to go, and that's to get infected. So we have one arrow from susceptible to infected. Now the rate of change for susceptible tells us, because people are leaving susceptible, is going to be negative, right? We're decreasing the number of susceptible people. So if you call the susceptible people S, as a variable S, that means that ds by dt is minus R1 or minus R out. There's a rate of people leaving. Okay, great. Now, what is this rate? What is this rate? Well, you could say that this rate depends on the number of susceptible people. The more susceptible people, the more likely that there are going to be more infections, right? It's one thing to have 5 people living in the state of Utah versus 7 million, right? You know, 5 people are probably not going to be infected. No one is going to be infected for those, right? So it makes sense that the rate of depletion or the rate of susceptible people becoming infected is proportional to the population of susceptibles itself. Okay, so I'm reasoning with this about this. This is something we can all understand. It's like real, true epidemiology. Okay? Okay, this is good, but not entirely right. Because for a susceptible person to be infected, they need to bump into an infected person. So how do you express that mathematically? S is the susceptible person, and I is an infected person. Mathematically, when they bump into each other, it's a multiplication. Not an addition or subtraction or division. So it's when S multiplies with I, that gives you a rate of interaction between susceptible and infected people. So really, an even better model than this is that the rate of people leaving susceptible and becoming infected is equal to minus, because it's depleting, some coefficient, beta, forget about that for a second, infected times susceptible. Now that makes sense, because if you have 1 infected person and 1 million susceptible, right, or like 10 infected people and 5 susceptibles, right, that scales it correctly. I times S. That product is going to give you an idea of the rate of how infected people are affecting susceptible, because it's really about the interaction between the two. Beta just adjusts how fast that occurs, because, okay, I times S, okay, how do you account for how much time they spend together, 10 minutes, 5 minutes, 17 minutes, right? What is the rate of viral dose, etc. So we lump all of that into the parameter beta. And then what we do to find beta, we go and make observations. We start collecting data, and then we try to fit this, and we find the right beta for that, okay? That's what they did during COVID. Like after like 3-4 months, we started getting better and better models at this. Okay, now infected, there is people coming in, okay, and people leaving, because eventually when they leave the infected, they're going to be recovered. Okay? But we know the rate at which they're coming in. It needs to be the same rate as people leaving from susceptible. So the rate of people coming into infected is exactly plus beta IS, right? Because the rate of people leaving the susceptible is minus beta IS. So the rate coming into infected is exactly plus beta IS. It needs to be positive because it's coming into the infected compartment, right? But there's also some people leaving from infected to recovered, okay? So we're going to have a negative term. Let's say it's some rate coefficient gamma times the number of people who are infected. So that's the rate of people leaving the infected compartment, the infected department store, at some rate gamma. I don't think we can do any better there because the rate of people leaving the infected category, you're going to assume that just the body is going to take care of itself, hopefully, and then 14 days, for example. That's how you adjust gamma. You figure out the rate of how quickly you're going to recover from the flu, from COVID, from a cold, or whatnot, okay? So that's how you adjust gamma. And then finally, once you're recovered, yay. There's only one option for recovered, and for it to increase over time. So its rate of change is only positive, and it's exactly equal to how many people are leaving infected, which is plus gamma I. Okay? Yes? So how about you develop a model for that? And that was going to be my next statement. Okay? So if you want, go ahead and develop a model of your liking. Okay? I've had people add hospitalizations, vaccinations, deceased, multiply infected, never infected, masked, like over the years, and they would submit it as like a mini project, I'm not promising you anything, but you might get a perk out of it. It's if you feel like you need a bonus thing, just take this and add a couple of compartments and see what happens. Okay? See what happens, all right? But this is the minimum, the simplest model you could do for pandemics and build a system of equations. So now, we do have a system of equations. ds by dt is minus beta is. I divided by n to normalize with the population n, because the previous example assumed a population of 1 and fractional population. So never mind the numbers, the coefficients, but what matters is that you have now 3 ODEs that you cannot solve them independently. You have to solve them together. Because the first ODE depends on I, the ODE for I depends on S, and the ODE for R depends on I. So okay, I guess that last one can be solved independently, right? Because there's no R in any one of those. But that's a system of initial value problems, okay? This is an example solution with these conditions, okay, where n is the population size, beta is the disease transmission rate in actual epidemiology lingo, and gamma is the recovery rate. 1 over gamma is the duration of infection. So for COVID, it's 14 days, 1 over gamma. So gamma is 1 over 14. And starting with some initial population and normalized by 1,000. So if you had 1,000 people for the blue line and 1 infected, so 999 susceptible and 1 infected person, right? This is what's happening. They start interacting with each other. There's some delay, and then you start moving from the blue curve to the red curve and subsequently to the green curve. And this is what happens, okay? Now, this is important. That red curve is very important. So when you look at the y-axis, it's normalized. It's like a fraction. What we're saying is for this setup, at peak, at the worst case, 60% of the population, about 60% is infected. You see that peak over here? And when people say, oh, let's flatten the curve, whatever, that's what they're talking about. That red curve, they want to flatten it because our hospital beds, they don't have that capacity. If you learn what ER departments do, like for flu season, et cetera, it's like scary. Like, I hope I never get sick, because we don't have capacity for 1,000 beds or 1,000,000 beds. It's ridiculous. It's not economical. It will cost a fortune, and they're going to be unused for most years. So typically, peak capacity for hospitals is like maybe 10% of a population. They all get sick. So what happens when you get 60% of the population sick and needing hospitalization, you overwhelm the system, right? So with the discussion about flattening the curve, et cetera, they were talking about that rat curve. How could we kind of bring it down? The model I developed, and we were trying to publish it actually, was to study the effect of like social distancing or isolation for some groups of the population, or how you stagger it. So, you know, it turns out like if you go like maybe as you start peaking, you increase social distancing, so you bring down the curve. So rather than having just a peak, you would have something like that goes up and kind of flutters around and then dwindles down over time. So you don't have extreme restrictions, but you don't also have an extreme overload of the system, right? So you could try to add 2 compartments for in the model. Like if beyond an infection rate, you increase isolation, but then below that infection rate, you relax the isolation. You can add a couple of compartments and study how that works. Anyway. This is a great example for doing a system of ODEs, and we're going to do it together in Python. Now, how do we do it in Python? You express it in vector form. So odeint not only takes a single ODE to solve it, or a single dependent variable, it can take an array of dependent variables, and in other words, an array of right-hand sides as well. Okay? So if I were to write this in vector form, I just take my dependent variables s, I, and r, put them in an array, and therefore their right-hand sides, I also put them in a vector or an array. And that's all you have to do. So now phi, or the dependent variable, becomes a vector, okay? And the right-hand side also becomes a vector, all right? Okay, are you guys with me? I feel like, you know, I've lost you, but I hope you are with me because this is useful, okay? It's going to be useful. It's going to be on your final exam. All of this is going to be on your final. I'm going to. All right.
But as soon as we have those constants known, right?
Yeah. Yeah, we're gonna play with those constants. In practice, what I learned is that these epi people, they're always collecting data and they're always fine-tuning the model. Okay, but it does operate in its simplest form this way. So if you want to add, you know, deceased, hospitalized, etc., at a given rate, you start playing with that and explore that space of parameters. What happens? Yeah. We had a little app on the website too, where you could just kind of move some knobs around, see what happens with, you know, different parameters, different coefficients. Okay, so we will use odeint to solve a system of ODEs. Pay attention here, okay, because there's going to be some Python jujitsu. There's going to be some Python jujitsu here to understand how we solve this, okay? So what we're doing here is we're trying to solve this system of equations, okay? It's a system of equations written in a single equation, but it's a vector equation, where phi is a sequence of, or an array of dependent variables, and the right-hand side is an array of right-hand sides, okay? And what this means is d phi 0 by dt is RHS 0, and so on and so forth. Okay? Each one of those dependent variables. So odeint does that. Okay? Instead of giving it a single right-hand side, now you give it a vector of right-hand sides. Right-hand side for the first ODE, right-hand side for the second ODE, right-hand side for the third ODE, and so on. You could build this in a single routine, right-hand side for COVID, call it, and return an array of the first right-hand side, second right-hand side, third right-hand side. We'll do that in a minute. Okay? But that right-hand side, it needs to have the same order of the arguments. Dependent variable, independent variable, and whatever arguments you might want to pass. Phi 0 is still an initial condition, but now it's a vector of initial conditions. Because you need an initial condition for each one of those ODEs. Go back to the COVID example. You need an initial condition for the susceptible population, for the infected population, and initial condition for the recovered population. Okay? So it needs to be a vector of initial conditions. The time space is the same. It's just a time space. We're going to run this over 2 months or 2 years or 50 minutes or whatever. It's just a sequence like lin space. Okay? So for example, for the SIR epidemic model that I explained, this is what you would do. You would return, for the right-hand side routine, you would return 3 right-hand sides, 1 for each ODE, and you would provide 3 initial conditions, and you just provide a time array. Okay? All right. So now, okay, it went and solved it, but it's solving a system of ODEs. So it's going to return the solution for the first ODE at all times, the second ODE at all times, the third ODE at all times, and so on. So in fact, what it does, it's going to return an array or a matrix of this form. And the first column is going to contain the first ODE, the values of the first ODE at all times. In the second column, the value of the second ODE at all times. So that's the second ODE, all the way to the last ODE. Okay? So your solution is not going to be as easy as what we did with a single ODE where you had phi at all times. This is you have multiple phis at all the times. Okay? So to plot it, you would need to grab this one and plot that one. The way you do this is you do this splicing, and that's kind of the jujitsu I was going to talk about. So you take sol, you grab all of the rows at column 0. For this one, you grab all of the rows at column 1, and so on. That's how you do that. Same thing for that second one. Because you're going to plot this. You want to plot it. Versus, do you have a question? Okay. And then you do the plotting. Okay? And again, if the right-hand side has other arguments, you do the same thing. You pass all of these arguments. The same holds. Okay, so let's go ahead and use ODEint to solve this pandemic model, or epidemic. It's not really a pandemic for this model. Okay. So open up a new notebook, please. And seriously, if you want to consider building your own epidemic model or COVID model or flu or whatever, shoot me an email and I can work with you, kind of reason about it, see what you're thinking, and how just it's really easy once you draw these compartments, put arrows to each one, and you'll realize how simple that is. All right, so let's get the boilerplate out of the way first. And I'm going to need ODEint. Now I have a single right-hand side, but it's going to return 3 right-hand side, 3 values. All right. Define RHS. Let's say epidemic, and that's going to take a phi array, say dependent vars, all of the dependent variables. So now ODEint, instead of passing a single dependent variable, is going to pass an array of dependent variables. Okay, and it's up to you to treat them in the correct order, how you want to order them, phi 0, phi 1, phi 2, or however you assign the meaning to those. And then time. Okay, and for this, let's see, should we pass different arguments? Okay, let's do total population, beta and gamma. So those are the parameters here in this SIR model. Okay, I need n, beta, and gamma. I'm passing those in. Why? Because I need to change those values a lot. So I'm not going to go back to the right-hand side and edit them. I'm just going to run ODEint over and over again with different values of those parameters. Okay, so it's easier to pass them as arguments. Okay. Now this is important. I am going to order, I choose, you have the choice to order those variables however you like. But once you choose that order, lock that order in. Dependent vars is just an array that contains 3 variables in this case. Could be S, I, and R, or RIS, however you choose. Where do you choose that? Right here. I'm going to say that my first value in dependent vars is going to be S, or the susceptible population. So, susceptible. Okay, and then the second one, I want it to be the infected, dependent vars 1. And the third one is the recovered, dependent vars 2. I renamed them so that I can make sense of what I'm working with, okay? Susceptibles, infected, and recovered, okay? If you change the order, if you put I in the first one, etc., you better make sure that you're passing the right-hand sides in the correct order as well, okay? So first dependent variable, we locked in the price. We locked in the meaning that the first dependent variable corresponds to the susceptible. So when I return the right-hand side, I'm going to return the right-hand side for the susceptible. Okay? So RHS for the susceptibles is equal to minus beta over n. So I'm just typing this equation. Couldn't be easier. Minus beta over n times I times s, okay? Times I times s. And then right-hand side for the infected is beta over n times I times s, right? Minus gamma times I, people leaving the infected, and RHS recovered is going to be gamma times I. And then I'm going to return simply an array, RHSS, RHSI, RHSR. This is how we chose the order. If you swap these in any way, you're going to mess up the meaning here. Okay? Because the first one, this is contained, it corresponds to the right-hand side for whatever you chose here for the meaning of this, okay? So the first ODE, this determines what your first ODE is. We chose that the first one is going to be S, the second one is going to be infected, the third one is going to be recovered. If I change the order, I have to change these here so that I stay consistent, okay? Be careful when you do that. For simplicity, just follow the order you wrote the equation in. If you've met with me before, you come up and show me code. I'm like, I tell you first, show me the math. What are you solving here? You need to write the math so you have a guide of what you're doing, not just shooting darts in the dark. Okay, that's it. That's it, guys. So now we can start kind of messing around. The rest is just post-processing, really. So let's take a population of 2,000 people, let's say, initial population. And we will do the initial infected is one person, okay? One person infected. Okay? And then initially R0, 0 people, 0 recovered. So that means my initial population of susceptibles is the total population minus I0, right? If I have 2,000 people, one of them is infected, so I have 1,999 not infected, right? So that gives me the initial condition for the susceptible. I'm going to choose beta equals 0.6, and gamma, you can change these numbers, 1 over 14 days for COVID, supposedly. And then T end is equal to 100 days. So the units for this system of equations, and that depends on the parameters really, is in days. Okay, so time is in days. ds by dt, it's number of infected per day, okay? Not per minute or second. Then let's say t is np dot linspace. Linspace, let's go from 0 to t end and do 100 points. Okay. All right, so now we can call ODE int. Sol, my solution is ODE int. And I'm going to call the right-hand side epidemic. I'm going to give it the initial conditions S0, I0, R0. Also, this determines the order as well. So this should be consistent with how you planned your right-hand side. SIR, that's how we planned it. Right-hand side S, right-hand side I, right-hand side R. And we're going to give it the time space, T, and we'll give it some args, which are the number, the population, total population, beta and gamma, right? So what did we do here? Let's see. We did n, beta, and gamma. So n, beta, and gamma. Okay? All right, let's see if it runs. Yay, it runs. Okay, so let's do some plots now. Give you also a second to catch up. Okay, so S is going to be contained in the first column. So it's going to be sol 0. I is going to be in the second column, which is sol 1. And the third column is going to be recovered, sol 2. Okay? And now I can plot this. So let's do it real quick, and then we make it beautiful. plt.plot time S, label equal susceptible, and then plt.plot time. We're going to plot the infected. We're going to make them in red because they're infected. Susceptible, make them in blue. Okay, red for infected, and label is equal infected. plt.plot T and recovered, and put those in green, and label is equal recovered. plt.grid. Yay! Okay, let's see. Let me scroll up. Sorry. Like excited. I got it. I don't care. Let me see if I can make this a little bit. Wow. Okay. Here. It's good. Yes? No? Ooh. ODE into excess work done on this call. Ooh. Okay. It's RHS SIR, and then ODE int T excess work done.
Like, is it the number of...
No, that's nothing. That's not much at all. Really. Yeah, so
My mouse is weird.
it could be your, so kill the kernel, let's kill the kernel. Could be your version of ODE int or scipy.
Okay.
But I think it's giving a solution though. Can you plot it?
Yeah.
Yeah. Value error.
Saying
Oh,
X and Y must be in the same dimension.
okay, so there's an issue going on here. I probably would want to spend some time debugging it with you.
Okay.
N0 beta gamma.
Here, I can-
Sorry, that's okay. I0 n minus I0 R0 is 0. That's weird. Yeah, it should just work.
Yeah.
Dependent var 0 1 2 beta over n.
What if I print? Can I print the
Solve.
solution?
You can. Yep.
Yeah,
It has a solution on it in it.
Apparently.
So yeah, I don't know what's going on. So
Oh, but then it
it worked. So
it
now
just said nothing.
run it. So plt.plot s sol comma semicolon comma 0. Okay, that should work. Okay, so how we doing? Okay. Play with the parameters now. Change gamma. Gamma has to do with the recovery rate. Okay, instead of 14 days, make them sick for 60 days or like 30 days, right? Like do function research, whatever, and make a virus that, you know, vicious. Okay, so let's scroll up and see what's going on. Yes, so you need a comma after the semicolon, right? Yeah, because you're taking the first, all of the rows, column 0, all of the rows, right? So this one is all of the rows, the first column. All of the rows, second column, and so on. Okay? Everyone gets sick in the end. Yeah. Eventually, yeah, everyone is going to get sick. You have to add a compartment where people never get sick or they don't interact with the, so who are, yeah, it's not really that hard. So add a compartment. So what I did when this came out, I added a compartment for socially isolated. And I had two arrows, one going in and one leaving it. And I never got everyone, not everyone got sick. Yeah. Or you could add some population who is like, Iron Man or something, like never gets sick.
So just incorporating a def term. If we have, a def rate of alpha, the def is alpha times the infected, right?
Yeah, but you are also,
Yeah, right. So then the rate then the infected is minus gamma times I minus alpha times I, right?
so yeah, if you add a compartment for deceased, that is going from infected to deceased, yeah, so that is going to decrease, so you need to change the,
decrease susceptible and infected, right? By the
well, not necessarily the susceptible, susceptibles is going to infected, that's it, right? It's not going,
Oh yeah.
right? So you have to take out from infected, draw the compartments if you want,
It's just taking out from infected.
from infected, yeah, yeah.
Alpha equals
Pardon me?
0.05.
Dark just real quick. This man is just a mad scientist. It's just like,
Mad scientist. Did you guys get it? Yeah. Okay, how are we feeling about the code? You guys got it? Yeah? Oh, yeah, looks great. So now you can play around with like gamma and beta and see kind of how the population changes. Okay? All right, good. You got it. How about you guys in the back? I feel like you're so far away from me. I want to spend some time with you here. We're good? Yeah? Okay, perfect. So you can play around now with these infection rates and, gamma and beta. Oh, that's interesting. What did you change? Could be in your... Yeah, it shouldn't go flat like that. Right-hand side, SIR, gamma I, beta, and minus I0, beta is 0.6. And we did N beta gamma, right? So yeah, that's correct. Yeah, that's weird. Why would it do that? Here, there you go. Good catch. You got it. Okay. How are we feeling? Bearded dad. You like it? Okay. All right, so now that we've conquered, we created a ultra virus in Python, you can go home, okay?